Okay, we continue from where we left off, where we introduced the two canonical forms. We introduced the two canonical forms. We have the SOP and the POS. You need to understand. You need to understand how you can come up with an expression using those two forms. How you can come up with the expression for SOP, the mean terms is also called the sum of, much better writing, sum of mean terms. The POS is also known as product of max, product of max terms. How do you identify mean terms? How do you identify max terms? Mean terms as such, mean terms are included in the SOP expression in such a manner that the function is an output of 1. Here we have the function has an output of 0. That's how you identify your mean terms, how you identify your max terms, specifically from the truth table. So we know already there are ways to go from an expression to the table. Now there is need to know ways to go from the table to the expression. What type of expression? Either using these two forms, the SOP and the POS. These canonical forms will be useful as we move. We'll see where they will be useful. Right. Now we go into conversion. Conversion of, we have conversion of SOP from standard to canonical form. Standard to canonical form. Canonical forms are easy to work with. If you have a function which is like this, x, y, z, x, y, z, x, y, z. If you have a function like this, it is easier to work with. Why? Because it has all the three variables x, y, z in each component of the expression. All the three x, y, z are available. It is, however, very difficult to work with something like this. In the expression, the whole expression, yes, you have three variables, x, y, z. However, in this expression, in this component of the expression, you only have two variables, x, y, x and y. The other one, x and z, the other one, y and z. Why is it difficult? It's not that difficult, but it will be easier to use this one. Why? Because from the function or from the expression, I can go on to write, maybe start with a shorthand notation directly from the expression. How easy is it to work with? Directly from the expression, I can start doing this. Watch. Help me come up with the shorthand notation there for those who understood. What is F? Shorthand notation. For those who understood, how do you get F? F is goes to sum of mean terms. This is 0, 1, 1. What is 0, 1, 1? I need a number here. Shorthand notation. 0, 1, 1. That's a 3, right?
3, yeah.
That's a 3. We have a 1, 0, 0. That's a 4.
4.
We have a 1, 0, 1. That's a 5.
5.
That's a 5, right? Right.
Yes.
I can go directly from the expression and I go to the shorthand notation. From the shorthand notation, I know my function is equals to 1 for which mean terms? For 0, 1, 1, for 1, 0, 0, for 1, 0, 1. I know if I can draw a truth table for this, the function output will be 1 if the input variables, they are 0, 1, 1, they are 1, 0, 0, they are 1, 0, 1. All these three coming from this expression. Is it like this? No. This one coming from this one, and this one coming from this one. 1, 0, 1. Yeah. And the rest are zeros. And the rest, the output will be zeros. So from the expression, I can find the shorthand notation. I can find the truth table. I can easily go through that process. But if you have a function like this, it can be or may not be that difficult to maneuver. You need to add something there. You need to add some flash. You need to add another variable there to make it complete. Another one here, another one here. So standard to canonical form conversion. How do you do that? This is the standard form. But how do you convert it to canonical form? Why we need to convert it is exactly what I just explained. Why we need to convert from standard to a canonical form is exactly what I just explained uh, a moment ago. Now, how do you do that? I have an example, a function f uh, which is equal to x, y plus y, z. How do you convert that into the canonical form? Right. How do you do that? We know that the function is three variables, x, y, z. We know that the function is three variables, x, y, z, x, y, and z. The first term, xy, is missing one term. And the second term is also missing one term. How do we add? How do we add that one term? We can make use of the rules which we already learned. With the rules which we already learned. All right. Xy can be the same as xy z plus z bar. What is z plus z bar? That's a rule there.
1.
It's equal to 1. So if we can replace 1 with z plus z bar, it will be perfectly fine. Here we can have yz is equals to yz plus, nope, x plus x bar. So if we can combine these two and expand, we can have f is equals to xyz plus xyz bar plus here now it's xyz, this one. Then we have plus x bar y z. Okay. Now there's another rule which can come into place there. What is x? What is x plus x? What is x plus x? Another rule. Participate. I'll wait. I have the
X.
time. X plus x is equal to x. So it means if I add this and this, it gives me XYZ. If I add this and this, nope, it's not the same. So I have here XYZ plus XYZ bar, this one, plus X bar YZ. So the function f can be reduced to the function f can be reduced, not reduced, can be expanded. Function f can be expanded to xyz plus xyz bar plus x bar yz. It can be reduced to xy plus yz. So using the same rules, you can go from xy plus yz to this expanded thing. You can go this other direction using the same rules which we introduced a week ago. You can go both ways. But now we need the rules to come up with this canonical form. Now we have all the three variables for each component. And with that, we can now easily interpret the circuit we are given here. We can now easily interpret the circuit. Now we can put our F in this form. Then we can go to the table much easier than if we had this one. Right. Give me the numbers. I need the number. 7.
110 is 6.
6.
011 is 3.
So we have 3, 6, 7. From this, it's way easier to understand than having a function like this one. Because from here, I know this is a sum of midterms. I know there's an output 1 here, there's an output 1 here, there's an output 1 here, and the rest, they are zeros. You cannot tell that from an expression like this. xy plus yz. You cannot. How you can tell is by going through the truth table. If you didn't learn, if you didn't understand how we can come up with this, you can go and draw your truth table G, which is a very long process because you need to find xy, you find yz, you then add the 2, you have 8 outputs, you have all that. Then you find what are the outputs, where is the output 1, where is the output 0. But nope, if I use canonical forms, I can easily get this expression. And from this expression, I can identify where my outputs are 1s, where my outputs are 0. Where my outputs are 1s for sum of midterms, here we are. If it is product of max terms, then we will be having zeros here, zeros here, zeros here. If we were to change here. And that's how you use the canonical forms, sum of products and product of sum in solving, analyzing a problem when given a problem, the analyzing process. That's how you deal with it. Canonical forms, Boolean algebra, simplifying, and all that other stuff. All right. I'm a bit tired. So you all do the talking now. Comments, questions, anything. While I take a breather. Unmute yourselves. Right. With that, I make the assumption that the 30 of you understood exactly what I was talking about here. So we continue. We now move to what we call kernel maps. What are kernel maps? What are kernel maps? This part is where we talk of minimization. It is another way of minimizing a circuit. Kernel maps is one way of minimizing a circuit. We talked of Boolean algebra as a set of rules which can be used in simplifying circuits. Another way of doing that is using the kernel maps. Definition: a kernel map provides a systematic method for simplifying Boolean expressions. Kernel maps, systematic method for simplifying Boolean expressions. If properly used, it will produce the minimum expression. If properly used, it will produce the minimum expression. Each row in the truth table is represented by a square. So let's start with the answer. This is basically a kernel map for a 2 by 2 variable. Is it 1, 2, 3, 1, 2, 3, 4? It can be like this: 0, 1, 0, 1, 1, 0, 0, 0. Here we have this is A, this is B, C. This is an example of a kernel map, right there. I will explain it. As you see it, what does it represent? So this part is the A's, the zeros and ones, and this part is a bit all over the place. So this is B, C, with 0, 0, 0, 1, 1, 1, 1, 0. That is a typical kernel map. Each, right, that is the kernel map. Each row in a truth table is represented by a square, and each square represents a minterm. Right? Each row. So if we have a truth table of how do I cut this? Clear, no, so select. Unfortunately, I think I cannot cut this. Okay, let's continue. Wasting my time. Yeah. Right. Each row in a truth table represents a square. So here we have, from our kernel map, I can identify 3 variables A, B, and C. What does 3 variables mean? 3 variables mean we have 2 to the power of 3 possible outputs. That is 8 possible outputs: 0, 1, 0, 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. I need to move this one. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 1. All right. What is our function G? Each row in a truth table is represented by a square. So each row, this row 0, 0, 0, this is the row. Its output x is represented by a square in the Carnot map. That's why we have 1, 2, 3, 4, 5, 6, 7, 8 squares. Each row is represented by a square, right? Each square represents a min term. Each square represents a min term. So my min terms, Edu, I think we now know them, how we can identify those min terms. All right. So for the min term 0, 0, 0, this is min term M0, min term M0. What is the output? Where can you identify where the min term 0, 0 is and what is the output on my Carnot map? This is min term 0, 0, 0, 0. So we have A 0 here. We have B, C 0, 0, 0, which corresponds to this square. For the min term M0, 0, 0, 0, the output is 0. Each row is represented by one square on the truth table, on the Carnot map. Each row in the truth table is represented by one square in the Carnot map. So this row 0, 0, it is being represented by this output 0 in the Carnot map. So now your participation for 0, 0, 1, what is the output? 0, 0, 1, what is the output?
1.
1, 0, 1, 0.
Zero.
It's 1, 0, 1, 0. It's 1. For 0, 1, 1,
Zero.
0, this one. This is 0, 1, 1. We have 1, 0, 0,
1,
1, 1, 0, 1, 0,
0,
1, 1, 0, 0, 1, 1, 1, 0. So, provided you are given a truth table, provided you are given a truth table, you can go on and find your Carnot map. And this is how you find it. Each row in the truth table is represented by a square in the Carnot map. Right, let's stop there. Squares are arranged in such a way that simplification of a given expression is simply a matter of grouping the squares. All right, these squares, the squares in our Carnot map, they are arranged in a certain manner. The manner you need to claim it, you later on understand it with practice. How you claim it, we have, if you have three variables, if you have three variables, A, B, C, two of the variables, I choose BC in this case. Many people, they can either use A, B, then C as one variable. Others can use A as one variable, then BC. So for me, I'm using this form where A is one variable with 0, 1. A is one variable with 0, 1. Then BC, it is arranged in this manner: 0, 0, 0, 1, 1, 1, 1, 0. It does not change. 0, 0, 0, 1, 1, 1, 1, 0. It does not change. Just a minute. All right. So I was saying each row is represented by one square on the Carnot map. How do you arrange those squares? This is the way you arrange them: 0, 0, 0, 1, 1, 1, 1, 0. They are arranged in such a way that there is only one bit difference between the two changes. So if we have between the two variables, if we have, if I can name them, okay, right. Here we have 1, 2, 3, 4. If we change from 1 to 2, only one variable changes. This one, it changes to 1. When we move from 2 to 3, this one changes 0 to 1, only one change. When we move from 3 to 4, this one changes to 0. They are arranged in that manner so that it helps simplification. It will be much easier if I can say 0, 1, 0, 0, 0, 1, then I go 1, 0, 1, 1, 0, 1, 2, 3. It will be much easier to arrange those variables in this manner. However, it does not solve our problem of the why part. Why we are doing this? Why we are doing this is for simplification, simplifying a circuit. You cannot simplify a circuit if you have your variables arranged like this. Because from 0 to 1, yes, there is one change, okay? From 1 to 2, however, there is two changes here. 0 changes to 1, 1 changes to 0, which should not be the case. So when you are arranging your zeros, your 0 1s, your 1 1s, your 1 0, remember that there should be only one change of the bits in the variables you are using. So you can now go from the truth table to the Carnot map. Likewise, you can go from the Carnot map and formulate your truth table. Now, if n variables, the number of squares is equal to 2n. For n variables, so if you are given n variables, for example, here we have 3 variables, a, b, c. The number of squares in your Carnot map, they are 8 squares. 1, 2, 3, 4, 5, 6, 7, 8. The number system in the Carnot map is based on the gray code. I just explained that. The numbering of the Carnot system, the numbering system in the Carnot maps is based on the gray code. If you can remember the gray code, we mentioned that change of one bit between two numbers. That is the same system we use in numbering in the Carnot systems. Numbering here, this is gray code. It is not the numbering, normal numbering 0, 1, 2, 3. Right. Two variable maps. Examples. We have a 2 variable map with us. When we talk of 2 variables, these are 2 variables, x and y. So our truth table, we have 0, 1, 0, 1, 0, 0, 1, 1, 0. We have a function f, which is 1, 1, 0, 0. Can anyone give us an operation used to find that function? Is there an operation? What type of gate is used to find that f output? Question 0, 0. Inverse 0, 0. Anyone with an idea? Nope. Is that an AND gate? Nope. No OR gate.
NAND gate.
NAND. 0, 1. That's a 0. It should be a 1. It's not a NAND gate. I think it's not amongst our primary gates. I think so. It's not a NAND. Because if it's a NAND, this is 0, not. It should be 1 here. All right. It's none of the primary gates. I think so. So we can continue. Now, we have our truth table for 2 variables, x and y, with the output function f. How can we draw the truth table? The truth table for this one, it has 4 outputs. 4 outputs, it means 4 squares. So we start with this, and we have this. We put our two variables x here and y. Our two variables x and y can only be zeros and ones. Okay. Now, what output comes here in this square? Help me. For participation sake, what output comes on this square?
1.
1 here.
1.
1 here.
0.
0, 0. Question. Is there anyone amongst you who doesn't get how we are coming up with those numbers so that we can finish it in class here? Anyone who don't understand? Nope. Everyone understands where these numbers are coming from. So that is an example of a 2x2 Kano map. How do you construct the Kano map? This is how you construct it. Now to the simplifying part. How do you simplify it? Let's say reading K-maps. How do you simplify? I want to start with this two variable map. How do you simplify? Or how do you read the K-map? Right. The variable which remains constant is 0 along the cell is written as the complemented variable. And the one which remains as 1 is written as the non-complemented form. All right. The one which remains at 0, let me try to put this out in a much simpler way. Variable which remains constant as 0 along is written in complemented. The one which remains constant as 0 is complemented. The one which remains as 1 is not complemented, so it is non-complement. All right. From there, you group the variables. You group the variables which are ones. Step number 1 on reading, group all the ones. Combine ones in groups. How do you know which groups to combine? All of them should have a power of, starting with a power of 2, 2 to the power of x. So you can have group with 2 terms, 2 to the power of 1. You can have a group with 4 terms, 2 to the power of 2. You have a group with 8 terms, 2 to the power of 3. In this example, we can group these ones. 2 to the power of 1, we have only these ones to group. I can group those two. Now, after grouping, you then come to apply here. Where it remains as 0, it is complemented. Where it remains as 1, it is non-complemented. Where, if we move from here to here, is the variable constant? I need an answer. If we move from here to here, is the variable constant? Nope. It is not, because the variable y changed from 0 to 1. So we cannot use that one. However, the x variable, it did not change. Where we made our group, this variable did not change. It remained 0. So this variable remained 0. We put it in its complement form. It means this function can be represented by x bar in its complemented form. Another example may be for understanding. Another example for understanding's sake. For understanding's sake. All right. Let's try a 3 variable map. We have a function f, which is equal to sum of products 1, 5, 2, 6, 7. All right. You can either go to the truth table, then go to the kernel map. I've just taught you how to go from the truth table directly to the kernel map. But if you understood how to manipulate this notation, it means it will be easy to identify how you can come up with your kernel map. So this function, it is given, it has 3 variables. We already mentioned that. There's 3 variables. What does it mean? It means it has 8 possible outputs, 2 to the power of 3. With 8 possible outputs comes 8 squares. Our kernel map, we have 8 squares. 1, 2, 3, 4. Now, to the variables, we have our variables. Let's use A. We have A and B, C. For A, we only have 0, 1. Here we have 0, 0. Here we have 0, 1. Here we have 1, 0. And lastly, we have 1, 1. Is this correct? Is this correct?
Yes.
Yes.
It's not
No.
correct.
No, it's not correct, sir. You have to
So
put 1.
0, 0, 0, 1. Here we have 1, 1, 1, 0.
And then 1.
All right. This is how we come up with the kernel map. Now, directly from the notation I just gave you, you can identify where the ones are. How? We know that if you use this sum of products, sum of min terms, it means the outputs f is equals to 1, f is equals to 1 here, 1 here, 1 here, 1 here. It means f is equals to 1 for what min term? What is 1? 1 is 0, 0, 1. What is 5? 5 is 0. Nope. What is 5?
1, 0,
1, 0, 1.
1, 0, 1.